Did you manage to fill out the tutorial of last week?
What?
The tutorial last week?
Yeah, last week I just feel uncomfortable and didn't come.
What?
I just feel sleepy.
No, it's fine. You can, right? You can not come, but just to know that you was able to feel it fine and that you don't have anything that you didn't understand.
Oh,
Okay. So today we will go through on Bose-Einstein condensation. Okay, so right, you saw in the lecture and also in the pages of the tutorial of last week that
last week we can't start the lecture, doesn't it?
yes. So maybe you saw it 2 weeks ago in the lectures. I completed the lectures or not yet?
You told me what is that? I will.
Okay. So the average number of particles in a specific energy level for system of bosons is let's say the average number of particles for some energy level is 1 over exponent of beta epsilon minus mu minus 1.
Oh, this morning.
Okay, good, great. So when this is, let's say, okay, so fine, this is our number particles in average in some energy level. So the total number of particles, the total number of bosons in the system is just summation on all these levels. Right? So this is the total particles in the system, and this is the average number of particles in a specific energy level. And when we're summing up on all possible levels, we will get the total number of particles, the average total number of particles in the system. Okay, so we can say such a thing. We want to see here something very specific. Okay, so we want to take the most extreme case and say, okay, we can take this value, the exponent of beta mu, okay, that we called it, label it in small z, and if this value goes to 1, okay, so this summation will get its maximal value. Okay, so let's take this extreme case that we say, okay, the maximum number of particles we can get in the system is with this this equation. Okay, when this exponent go to 1, and then the maximum number of particles we can get Okay, so we have here some constant that depends on the values of the system, its volume, and we have not pi, we have 2m kBt in the power 1/2 divided by 4 pi h bar in the third, and we have here the zeta function, and we have the gamma function. Okay, so gamma function, right, you know gamma function.
I know what it is, but I don't remember what exactly is a formula.
Okay, so gamma function, we calculate it recursively, and so the value of gamma function of n equals to n minus 1 gamma function of n minus 1. Okay, so for whole numbers 1, 2, 3, 4, and so on, we get here a factorial function. Okay, and for half numbers, so we get something a bit more complicated, but we know that gamma function value of half equals to, if I remember right, it's the square root of pi. And then we can calculate any value we want of the gamma function with this recursive formula. So this is the gamma function, so it has known values, and the zeta function defined by integral, so it's equal to 1 over gamma function of this value p times integral from 0 to infinity of x p minus 1 divided by exponent of x minus 1 dx. So also here we get some value. Okay, we just need to calculate this integral with 1.5, and we get its value. Now this integral has a finite value. Okay, it doesn't go to infinity, so it converges only when p minus 1 is greater than 1. Greater than 0. Okay, so we can see that for our value, right, for in the maximum number of particles in the system, we have a finite value for this integral. Right, so that means that all these size is a finite size. Right, because all the functions are have finite values. Okay, so usually this is a good thing, right? That we have the integral that doesn't go to infinity. But in this case, it creates a problem. So we know that the bosons don't have any constrictions for being in some energy level, right? So if we have a system of some energy levels, we can just keep inserting bosons to the system without any limitation. Okay, so now our system, right, we have energy levels from some epsilon equals to 0, and it goes up to infinity. Okay, so theoretically, we can have any numbers of bosons we want in this energy level epsilon equals 0 without needing to invest any energy from outside. We just keep inserting particles to these levels, to this level, right? So we do expect to get some infinite number for our maximum number of particles, because we always can keep and inserting more particles to the system. Okay, so in order to correct this value, we're doing the next thing. Okay, so we say, okay, this value is fine, is correct, but only for the levels that are not with 0 energy, that are not epsilon equal to 0. So we said this thing. So, okay, the total number of particles in the system will be equal to this value. So now we will call it n excited. Okay, only particles that are in excited level of the system, not in the ground state. And then manually we will insert here the number of particles in the ground state. Okay, and this number of particles will be equal to the average number of particles for the specific level of epsilon equal to 0. So we will take our Bose distribution and just insert epsilon equal to 0, and then we have here 1 over exponent of beta 0 minus mu minus 1. Okay, but why can we do this correction? Why it works, or why this didn't work? So this number of particles, when we're summing up on all our possible levels in the system, okay, so we do it with an integral. So we have here some constant, okay, that depends on the values of the system, its volume, its temperature, and so on. And then we have here the integral on the Bose distribution. So we have beta epsilon minus mu minus 1, and then we need to insert the density of states, right? So we have here times square root of epsilon. Now, when we're talking about epsilon equals 0, so we actually get that this this term for epsilon equal to 0 doesn't give us anything in the integral, okay? Because the density of states gets to hold this term to be 0. Okay, so for epsilon equal to 0, we need to manually calculate the number of particles in this level. Okay, without this density of states that works fine for the levels that are not epsilon equal to 0. Okay, so when we don't have this N0 term and all our particles, bosons in excited states, okay, this is for us a classical gas. Okay, regular gas, we're just considering it as classical gas. When we're starting to see this term of N0 becoming bigger and significant, so we call this phenomenon Bose-Einstein condensation, that we have many particles that are being at the lowest level of the system. Okay, so let's see how this depends on the temperature. So we have here some phase transition, right, from a classical behavior to a quantum behavior. So we want to find this temperature that we see the phase transition occurring. So we can define this T critic, and we want to find it. We know that in T critic, right, exactly in this temperature that we see a phase transition, we will get that the total number of particles in the system will all be in excited states, and for temperatures that are smaller from this critical temperature, we will see that we have this term of N0. Okay, we have particles in the lowest level of the system. Okay, so this will get us the critical temperature. So let's just take our total number of particles in the system, say it equals to the excited number of particles in the system, and see what temperature will give us this term. Okay, so the total number of particles in the system will be equal to this value, the number of excited particles in the system, right? But it will be in a specific temperature, the critical temperature. So this will be equal to V times 2m KB T critical in the power of 3/2 divided by 4 pi h bar in the third, and we have here the zeta function and the gamma function. So we can say that our T critic, we can extract it from here and write it in terms of the total number of particles in the system. So we get that the critical temperature is h bar squared divided by 2m, and we have here 4 pi m divided by v zeta function 1.5, gamma function 1.5 in the power of 2/3. Okay, so this is our critical temperature, and then we can see the ratio between the number of particles we will get in the ground state for temperatures that are smaller than the critical temperature relative to in what temperature we are. So we can write that N0 over N, that should be equal to 1 minus the number of excited particles divided by the total number of particles. Okay? And then we can write this value, the number of excited particles, using the critical temperature, and we get that this will equal to 1 minus T over the critical temperature in the power of 3 over 2. And we need to remember that all of those equations are valid only for temperatures that are smaller than the critical temperature. Or we can say small equal to the critical temperature. And then actually when we applying T equals to the critical temperature, we're getting that N0 equals to 0. Okay? Great. Okay, so for example, we want to calculate the pressure P for both gas in temperatures that are smaller than the critical temperatures and with mu equals to 0. So we want a specific chemical potential that equals to 0. We want the temperature to be smaller than the critical temperature, and we want to calculate this gas pressure. Okay. So for calculating a pressure for a system, right, we need its partition function. Okay, so what we know that the pressure of the system, we can calculate it as minus derivative of the current canonical potential or the free energy of Helmholtz relative to the volume. So we need to find this ground canonical potential. Okay, so we know the ground canonical potential is minus kVt ln ln of the partition function, and the partition function is a summation on all possible states in the system. Okay, let's not write it like this. So we want to calculate the partition function of this system, and we know that for both gas or Fermi gas, we don't calculate the partition function as usual, as summation on all possible states of the system, but we calculate the partition function for one energy level as a subsystem partition function, okay? And then use those functions to get our total partition function. Okay, so we know that a partition function for one energy level in both gas equals to 1 over 1 minus exponent of minus beta epsilon minus mu. Okay, and then the total partition function would be multiplication on all levels in the system of our subsystem partition function. Okay, and we use here multiplication and not power of, because our each level considered as a different particle of the system, because it behave differently. Okay, because the energy of this level is different, so they are considered as different particles in the system. Okay, so we have this value. So the total grand canonical potential of the system now gives us KBT summation on all energy levels, and we have here ln of 1 minus, let's write it as ZE minus beta epsilon. Okay, when this Z is what we define to be E beta mu. Okay?
Yeah.
Okay. So we're getting that our grand canonical potential, and then we can say, okay, we are given that the chemical potential equals to 0. So this value equals to 1. Okay, and then we're summing up this summation, and we get here KBT, and we do this integral on all possible energy levels, and we have here the density of states, and we have ln 1 minus E minus beta epsilon d epsilon. And now we need to solve this integral to get our grand canonical potential. Okay, so this integral is not straightforward to calculate. Okay, right, our density of states goes like square root of epsilon. So what we would do here, we will first calculate the pressure. Okay, we will conduct the derivative under the integral sign. Okay, and then we will calculate the integral. It will give us an easier integral to calculate. So let's first calculate the pressure and then solve the integral. Okay, so this is our chemical grand canonical potential, and now we can calculate the pressure by derive this potential relative to V. Okay, so we have such a thing. Okay, our density of states, right? Density of states of an ideal gas equal to some constant times V times square root of epsilon, right? So the density of state goes like V. So when we derive this grand canonical potential, when we derive this density of states relative to V, we get that its derivative just eliminate this volume, right? So we get it is actually equals to this density of states divided by V. Okay, because it's only eliminate this dependence on the volume. Okay, so instead of writing the whole density of states each row, we will just write it as density of states divided by V. Okay, because it gives us the same value. Okay, so now we can write the pressure as minus as kBt, and now after we did the derivative, we get here d epsilon divided by v. Okay, so we have integral from 0 to infinity, the density of state divided by v. This is from the derivative. Okay, and we have ln of 1 minus e minus beta epsilon.
What about the minus?
What?
P equals to minus d.
Right. Here minus, thank you. Yeah. Okay, so we have minus this this size. And of course we have here the d epsilon. Okay, so this didn't help us in calculating the integral at all because we just received the same integral divided by v. So now let's see what its solution, if we can solve it. So let's write now the density of states. Let's write it explicitly. So we have this, so it equals to minus kBt, the integral, and we stay here with 2m in the power 1.5 divided by 4 pi h bar in the third, and we have here square root of epsilon ln of 1 minus e minus beta epsilon. Okay, so we are not going to solve this integral. Okay, we will keep our answer in this form of some integral. Then we can solve it numerically, but for now we will keep it this way. Okay. So far it's fine?
Yeah.
Great. So we're moving to the next section. And now we want to calculate the heat capacity again for temperatures that are smaller than the critical temperature, because then we can take this gas as boson gas and not as classical gas. Okay, so we want to work in this area of temperatures still with mu equals to 0, and we want also to find the heat capacity for the critical temperature itself. Okay, so in order to find the heat capacity, we want the heat capacity in constant volume. So what is the heat capacity in constant volume? So we can calculate it by deriving the internal energy relative to the temperature with a constant volume. Okay, so in order to calculate this size, we need to find our internal energy, right? So the internal energy, again, we can find it from the grand canonical potential. It's a thermodynamic size of the system. So we can calculate the energy okay, so we have we can calculate it from the grand canonical potential, but we also can calculate it from in the direct way from our density of state. So we can say, okay, the internal energy is the value of energy each level has times the density of states, right? It's like an average. Okay, but here we need to insert as well the Bose distribution that tells us how many particles we can find in each energy level. Okay, so each energy level contributes this epsilon term, plus it contributes this epsilon terms that times as the number of particles that are in this energy level. Okay, if there are 2 particles in this energy level, it contributes 2 epsilon and so on. So we need to insert here the distribution, the Bose distribution, that tells us how many particles in average that are in each energy level.
כן, שלום. כן?
כן, עדיף להיכנס אחר כך, תודה.
אוקיי.
Okay, so this integral will give us okay, so we have all the constants from the density of states. So we have here V times 2m in the power of 1.5 divided by 2 pi h bar in the third, and we have here epsilon right from here, and we have squared epsilon for the density of states divided by epsilon exponent of beta epsilon minus 1 from the Bose distribution. And this is the integral we need to solve. Okay, so this integral we can solve because it has the zeta function definition. Right, so this integral is defined we have all the constants and this integral is defined as the zeta function of the value 2.5. So we have some constants from the integral. And the zeta function 2.5. Okay, so what happens here? So we take this value to be x, so it will match to the definition of zeta function. So if this is x, we do change of variables, get this constant out, and then remaining with the definition of zeta function of 2.5. So the definition of zeta function, right, is 1 over gamma function of p, integral from 0 to infinity, x p minus 1 divided by ex minus 1. Right, and we want to bring this integral to this form. Okay, so first we're dealing with the exponent. So we're doing a change of variables and saying, okay, x will be equal to beta epsilon. And then when x equals to beta epsilon, so epsilon will be equal to x divided by beta, and dx will be equal to beta d epsilon. Okay, and then we're changing variables and getting that epsilon square root of epsilon divided by this exponent will get the form. So let's see, we have x squared x divided by ex minus 1, and from here we have times 1 over beta squared beta, right? And then the epsilon goes to dx divided by beta. Okay, and then we have all the constants that doesn't depend on the x, and we can get them out from the integral. Okay, and in the integral we're keeping with so we have x in the power 1.5 divided by ex minus 1. Okay, and this gets to very similar to this form. We only need to find this p, right? So here our p minus 1 equals to 1.5. So p equals to 2.5. And then this integral will be equal, right? So this is zeta function of p, so it will be equal to zeta function of 2.5 times gamma function 2.5, because this constant. And we get this value. We're inserting here in the result for this integral and get this thing. Okay. Great. So this is the heat capacity for some temperatures that are lower than the critical temperature. And now we can get the specific value for the critical temperature. Okay, so what was our critical temperature? We calculated in the beginning of the tutorial, right? We wrote it as a term of the total number of particles in the system, right? And then we take this term, this long term, and insert it to this beta, to the temperature here. Okay, just inserting T equals to the critical temperature, this value. So we get that the heat capacity is 15 over 4 zeta function of 2.5 divided by zeta function of 1.5 nkb. Okay, so this is approximately equals to, so the zeta function has known values, so it's approximately equal to 1 over 1.925 nkb. Now this is interesting because we know that above the critical temperature, right, the gas should be classical gas. Should behave as classical gas. And we know that in classical gas, ideal gas, the behavior of the heat capacity equals to 1.5 nkb. Okay, so it's different from this value. So what happens, we can plot it like this. So this will be the critical temperature, and this will be the heat capacity in units of nkb. Okay, so we're expecting that for high temperatures, for classical gas, we know that this value goes to 1.5 nkb. Okay, and we know that at the critical temperature, so when this will get the value 1 when T equals to T critic. So in this temperature, we know that we get 1.925. So the behavior will be something like this. So we're starting with Bose-Einstein condensation gas, getting something like this. The heat capacity is getting greater until for the critical temperature we get to this value of 1.925. Okay, and then we know that at high temperatures the behavior goes to 1.5. So we'll get here something like this. So in the area of the critical temperature, the gas is still not perfectly classical, but as we increase the temperature, it will get more and more classical and get more close to this value. Okay, and this will be the behavior of the heat capacity.
So where is classical capacity from? The Einstein model?
No, so the classical heat capacity is from the model of an ideal gas.
Ideal gas.
Yeah, because okay, yeah, we deal here for boson ideal gas. Ideal gas of boson. So we just take into consideration its quantum nature of the particles, but we still assuming ideal gas that the particles does not affect one on each other. So the classical value just goes, it is just from the calculations of ideal gas in classical particles. Okay, and this we get from the assumption of quantum particles.
Oh, so why the classical function has a... Oh, I understand.
Yeah. So yeah, we just analyze it in the same values. So we know that at very high temperatures it will behave like classical gas, but around here, so it still has some quantum effects on the gas. Okay?
That's all?
Yeah,
Yeah,
that's all
thank you.
for today.
Thank you so much.
Great, you're welcome. You need anything from the board, or can I raise it?
Yeah, I have a racket.
Great.